So let us now talk about solution concepts other than those we have discussed till now. So till now we have looked at Nash equilibria, pure and mixed, and also we looked at the dominant strategy equilibrium. So when every strategy is strictly dominant or weakly dominant. Now we are going to look at some classical other solution concepts, which are also important to model reality. So first, let us look at this succession of pure and then mix. What does it mean? That we look first at actions being taken as they are defined, and then we allow for some independent randomization, and then we are talking about mixed Nash equilibrium. But sometimes the randomization can be conceivably dependent. So if I know that, let's say that I arrive at traffic, there is a traffic jam and we decide who is going to pass, or even a simpler example, when there is an intersection. So several people are at the same time at an intersection, and then who shall pass? At most one shall pass at a time in each direction. So I can say there are two equilibria, right? Either I pass or the one who crosses me. But it can be that we basically want to randomize. Now, if we don't want to crash, it's reasonable not just to randomize independently, but to randomize to dependently. So let's say, okay, let us together toss a coin. For example, we can have this coin called traffic lights. And then we see if the traffic lights say that I move, then I move. Otherwise, they say that you move. Of course, in reality, that's not random. That's something else. But that's the idea. So they can randomize in a correlated way, having a source of coordination. Now, it is still going to randomize separately, but they have some sort of coordination. Like a broker, such as traffic lights is in a way a kind of broker. A sort of a broker. Now, a further step would be that we randomly choose between various, so that we even randomize together. So one way that we randomize each one of us seeing some perhaps different signal. So I see some signal, or let's say the broker tells me the broker whispers to my ear some signal, and then I behave in some way, and maybe a different signal is whispered to your ear, and then you behave in a different way. Now those are dependently randomized choices, but each one randomizes separately. Now we can even think of randomizing together. So each one still has his own interest, but we randomize together. So we are completely free in how we depend on one another. We just toss a coin, and then a coin tells us the outcome of the toss, tells us which common profile we should take. And then we hang. So for example, we toss a coin and then said you do this, you do that, you do that. Another outcome of the coin or dice in general, many options, tells us we should do something else. Now we are not going to study the coarse correlated case in the lectures. We have done a little bit of that, and we'll probably continue on tutorials, simply because it's outside of our scope. But the more famous, and they're both important, of course, the more famous correlated is something we are going to study now, not to death, but we are going to give it a reasonable shot to try to understand it nicely. And another reason to study those is actually something which historically came after their definition. Now, as I said, after their definition, there was formally proven by means of certain reductions that computationally finding a Nash equilibrium, or even a mixed Nash equilibrium, say we know that there exists one, we always know that a finite game has a mixed Nash equilibrium, for example, from Nash's theorem, the computational problem of finding that is hard. It's so-called PPA complete. It's hard, and therefore defining a wider solution concept gives us hope that we will be able to compute that easier. So starting with a normal Nash equilibrium, with pure Nash, defining the wider concept of mixed Nash gave us hope of existence, which indeed was proven for at least finite games, for the mixed extensions of finite games. Now, defining the correlated equilibria gives us hope of not only existence, which is, of course, which is an immediate result of them including the mixed equilibria, but also gives us hope of an easier computation, polynomial computation. And funny enough, that hope is actually that's true. So it's possible to polynomially compute them, and therefore it's also possible to compute a wider range of coarse correlated equilibria. But again, we are not going to talk about the coarse correlated, besides definition, the basic stuff on the tutorial, and we are definitely not going to talk about computing them in an algorithmic manner. So that's just some little spark to whet your appetite to learn further. So there is a very beautiful algorithmic theory beyond that. It's also related to learning, because it's also provable that not only are we able to compute those correlate and coarse correlate equilibria, but we're also able to learn them. So the players, if they follow a certain learning dynamics, they're able to arrive at such an equilibria, at least approximately, in a polynomial time. And that's really practically interesting. So that's something which is important, non-trivial, but beyond the scope of our course. Now, another topic we're going to cover briefly is the topic we already touched upon in the tutorial, is the famous topic of strong Nash equilibrium. And that's another direction of extension. So that's not the direction of how we randomize, but that's the direction of what if players collude to deviate in a certain manner. What if they look at the utilities of others as well when they deviate? Because no collusion is something we assume till now, and that can happen, but that's not always realistic. So another important topic is modern coalitions which deviate. It's still non-cooperative game theory, it's not a coalitional one, but we do model some group thinking here. So this coalition-proof stability is something which is very important, practically important, and we are going to learn that. And finally, for this lecture, we're going to study evolutionary game theory. We're going to, again, to only touch, to like have a little bite of that. Now, that's a very important and beautiful and practically important game theory. You can also learn it on a popular level in, let's say, the Selfish Gene book by Dawkins, and there are other books which touch upon that area. So evolutionary game theory is a very practically important branch of game theory, where we model, as you can guess, evolution. So we model strategies, and the strategy which is currently most important grows in a certain way, and the strategy which is less important shrinks. And the players are actually populations. So the population well, it's not exactly the group which behaves according to a certain strategy, which has a higher fitness, will grow relatively to the group which currently behaves to a strategy which gives it a lower fitness. And so basically these models, these dynamics of behavior, where behaviors which give you more utility at a certain step provide you more support at the next step. It of course can model politics, it can model not only biological evolution, it can model many things, economical policies and so on. It can model this meme notion of Dawkins. So this is a mathematical model which can model many important, practically important phenomena. And a stable constellation of strategies is something which is going to be self-sustaining. So it replicates itself. It does not. It is optimal given that others are like that everyone behaves according to that strategy. Despite that, there may be some mutations, some agents who play differently, some animals or people or whoever who play differently. It still is the best response to what it is. Okay, so now I hope I've motivated you to those concepts which we are going to study. So first, we are going to allow for dependency around randomization, which is going to be formalized in the famous notion of correlated equilibrium. Then we are going to go and study the coalition proof stability, which is strong Nash equilibrium. So that's another direction. Not about how we randomize, but which interest do we take into account and who can deviate at the same time. And the last for this lecture is going to be which strategies are called evolutionary stable. So that's a glimpse into evolutionary game theory. Okay, so let us start with correlated equilibrium. And first, let us mention a little bit more about computation and learning of equilibrium. So the main part is that you want to model coordinated randomization. That the profile, not only we're not talking about how to define stability, we're talking about which profiles are we looking at. So Nash equilibria look only at pure profiles. Mixed Nash equilibria look at mixed profiles when every strategy is a mixed strategy, so it's a possible randomization on one strategy regardless what others do. You only randomize in your strategy. And the total profile is therefore combined. It consists of independent random strategies. Now we're going to look at profiles which may consist of somehow dependent strategies. Again, the deviation proof will be again the deviation of a single player. It's no strong proof. It's not a coalition proof equilibrium. But the profile itself allows us for correlation. Now, in addition, something we have not and we won't do in this course, but something for you to know in general, especially for people who like algorithms, machine learning, and so on, and economics, of course, because it's practical, or social sciences, actually, because social sciences are also a domain which can be modeled using game theory. So, in a general finite game, it can be proved that pure Nash equilibria are hard to find, even for two players. They're so-called PLS complete, so they're at least as hard to find as finding a local PLS is PLS is about local search, What does P mean? Let me recall this. Oh, I forgot what it means. Excuse me.